Question 1. Risk assessment procedures indicate a need to evaluate the lighting conditions in a manufacturing area where intricate assembly tasks are performed. Which of the following approaches best ensures compliance with occupational health and safety guidelines for lighting? Option A. Measure only the average illuminance level in the center of the work area. Option B. Measure illuminance at multiple points across the work area to assess both average levels and uniformity, but disregard glare. Option C. Use a generic good lighting benchmark based on general industry experience, without consulting specific task requirements or regulatory standards. Option D. Measure illuminance at multiple points across the work area to assess both average levels and uniformity, and evaluate potential for discomfort glare. The correct answer is D. Measure illuminance at multiple points across the work area to assess both average levels and uniformity, and evaluate potential for discomfort glare. Explanation. Scenario analysis. This scenario presents a common challenge in industrial hygiene, evaluating the adequacy of existing lighting conditions against established standards. The difficulty lies not just in taking measurements, but in interpreting those measurements within the context of regulatory requirements and the specific tasks performed by workers. A key challenge is recognizing that a single illuminance value may not be sufficient. Factors like uniformity, glare, and spectral quality can also impact visual performance and comfort, and therefore worker safety and productivity. The professional must discern which measurement and analysis approach aligns with the governing regulations and best practices for industrial hygiene. Correct approach analysis. The correct approach involves a comprehensive evaluation that considers not only the average illuminance levels, but also their uniformity across the work area and potential for discomfort glare. This aligns with the principles outlined in relevant U.S. occupational safety and health standards, such as those promulgated by OSHA and recommended by NIOSH and ANSI. These standards recognize that effective lighting is more than just brightness. It's about providing sufficient, appropriate light for the tasks performed without causing visual strain or hazards. Measuring illuminance at multiple points to assess uniformity and considering glare indices directly addresses the practical application of these standards in a real-world work environment. This approach demonstrates a thorough understanding of how lighting impacts worker well-being and operational efficiency, fulfilling the industrial hygienist's responsibility to protect workers. Incorrect approach is analysis. Focusing solely on average illuminance without considering uniformity fails to capture potential areas of insufficient light or excessive contrast, which can lead to eye strain, fatigue, and increased risk of errors or accidents. This approach is deficient because it overlooks critical aspects of lighting quality that are implicitly or explicitly addressed by occupational standards. Measuring illuminance only at the center of the work area is an incomplete assessment. It neglects the edges and other critical zones where tasks are performed, potentially leading to an inaccurate representation of overall lighting adequacy. This is a failure to conduct a representative sampling, which is a fundamental principle of industrial hygiene measurement. Using a generic good lighting benchmark without reference to specific task requirements or regulatory standards is unprofessional and potentially non-compliant. Occupational lighting standards are task-specific and often tied to regulatory requirements. Relying on subjective judgment or non-specific benchmarks bypasses the established criteria for ensuring a safe and healthy work environment, representing an ethical and regulatory failure. Professional reasoning. When faced with evaluating lighting conditions, a professional industrial hygienist should first identify the applicable regulatory standards, e.g., OSHA, ANSI/IES recommendations. Next, they must understand the specific tasks performed in the work area to determine the appropriate illuminance levels and quality criteria. The measurement strategy should be designed to capture representative data, including illuminance, uniformity, and glare potential across the entire task area. Analysis should then compare these measurements against the established standards, considering all relevant parameters. If deficiencies are identified, recommendations for improvement should be specific, actionable, and justified by the data and regulatory requirements. This systematic, data-driven, and standards-based approach ensures that the assessment is both scientifically sound and legally defensible, fulfilling the professional's duty to protect worker health and safety. Question 2. The risk matrix shows a moderate to high risk for acute and chronic health effects from exposure to a specific volatile organic compound, VOC, in a manufacturing facility. The facility operates 24/7 with varying production levels throughout the day. The primary goal is to assess worker exposure to ensure compliance with established occupational exposure limits and to evaluate potential long-term health risks. Which of the following sampling approaches best aligns with these objectives and regulatory expectations for industrial hygiene practice in the U.S.? Option A. Conduct a qualitative assessment of potential exposure based on visual observation and worker interviews. Option B. Employ a direct treating instrument calibrated for the specific VOC to provide instantaneous readings throughout the work shift. Option C. Collect air samples using passive badges that provide an integrated exposure measurement over a specified period. Option D. Utilize sorbent tubes followed by laboratory analysis to determine time-weighted average (TWA) concentrations for the VOC. Correct answer is D. Utilize sorbent tubes followed by laboratory analysis to determine time-weighted average (TWA) concentrations for the VOC. Explanation. This scenario presents a common challenge in industrial hygiene, selecting the most appropriate sampling method for a potentially hazardous gas in a dynamic work environment. The risk matrix, indicating a moderate to high risk for acute and chronic health effects from exposure to the specific gas, necessitates a robust and accurate sampling strategy. The challenge lies in balancing the need for reliable data to assess worker exposure against the practical constraints of the workplace, such as the nature of the gas, potential interferences, and the need for timely results. The correct approach involves selecting a sampling method that aligns with the identified hazards and regulatory requirements for exposure assessment. For gases and vapors, this often means considering both direct treating instruments for immediate feedback and sorbent-based methods for time-weighted average (TWA) exposure assessment, depending on the specific regulatory limits and the nature of the exposure. Given the potential for both acute and chronic effects, a method capable of providing accurate TWA concentrations is crucial for compliance with occupational exposure limits (OL) and for evaluating long-term health risks. An incorrect approach would be to solely rely on a direct treating instrument without considering its limitations or regulatory acceptance for compliance monitoring. While direct treating instruments offer immediate results, they may not always meet the accuracy or specificity requirements for establishing compliance with OELs, especially if they are not calibrated for the specific gas or are susceptible to interferences. Furthermore, they may not provide the integrated TWA data required by many regulations for chronic exposure assessment. Another incorrect approach would be to select a sampling method based solely on cost or ease of use, without a thorough evaluation of its suitability for the specific gas and workplace conditions. This disregards the fundamental principle of industrial hygiene to protect worker health through accurate exposure assessment. A third incorrect approach would be to assume that a single sampling method is universally applicable without considering the specific properties of the gas, potential co-exposures, and the objectives of the sampling program, e.g., initial assessment, compliance monitoring, leak detection. The professional decision-making process should begin with a thorough hazard assessment, understanding the physical and chemical properties of the gas, its known health effects, and relevant regulatory standards, e.g., OSHA GTLV. This informs the selection of appropriate sampling strategies and analytical methods. The choice between direct treating instruments and sorbent-based sampling should be guided by the need for real-time data versus integrated TWA data, the required accuracy and specificity, and the regulatory requirements for the specific substance and industry. Validation of the chosen method through calibration and quality assurance procedures is paramount. Question 3. Benchmark analysis indicates that a manufacturing facility's industrial hygiene program has been in place for several years with minimal documented changes. The program includes annual safety training records and a log of air monitoring conducted for a limited set of chemicals. The facility is facing pressure to demonstrate robust compliance with OSHA regulations. Which of the following approaches best aligns with the principles of effective industrial hygiene program management and regulatory compliance in this context? Option A. Conduct a comprehensive hazard assessment to identify all potential chemical, physical, and biological agents, evaluate existing controls, and prioritize program improvements based on risk levels and regulatory requirements. Option B. Prioritize the implementation of easily measurable and reportable IH activities, such as the distribution of personal protective equipment, even if these activities do not address the most significant identified health risks. Option C. Rely on the existing historical air monitoring data and training records, assuming that processes and exposures have remained consistent over the years, and update documentation to reflect current dates. Option D. Focus on increasing the frequency of documented safety training sessions and expanding the list of chemicals for routine air monitoring to create a more extensive compliance record. The correct answer is A. Conduct a comprehensive hazard assessment to identify all potential chemical, physical, and biological agents, evaluate existing controls, and prioritize program improvements based on risk levels and regulatory requirements. Explanation. This scenario presents a common challenge in industrial hygiene program management, balancing the need for proactive hazard identification and control with resource limitations, and the pressure to demonstrate immediate compliance. The professional challenge lies in interpreting regulatory intent beyond mere checklist compliance and applying a risk-based approach to program development and implementation. Careful judgment is required to prioritize actions that will have the most significant impact on worker health and safety, while remaining within the bounds of regulatory requirements and organizational capacity. The correct approach represents best professional practice because it aligns with the fundamental principles of industrial hygiene as outlined by regulatory frameworks such as OSHA General Duty Clause and specific substance standards. It emphasizes a systematic process of hazard recognition, evaluation, and control, which is the cornerstone of an effective IH program. This approach prioritizes worker health by focusing on the most significant risks and implementing controls that are technically feasible and economically sustainable, thereby ensuring long-term program effectiveness and compliance. It also reflects ethical obligations to protect workers. An incorrect approach that focuses solely on documented training without assessing actual understanding or the effectiveness of controls fails to address the root causes of potential exposures. This approach is ethically deficient as it prioritizes a superficial demonstration of compliance over genuine worker protection. Regulatory failure occurs because OSHA and similar bodies expect programs that demonstrably reduce risk, not just document activities. Another incorrect approach that relies on historical data without considering changes in processes, materials, or worker populations overlooks the dynamic nature of workplace hazards. This can lead to a program that is out of date and ineffective, failing to identify emerging risks. Ethically, this is a dereliction of duty to protect workers from current hazards. Regulatory failure stems from the expectation that IH programs are living documents that adapt to changing conditions. A third incorrect approach that prioritizes easily achievable compliance metrics over significant health risks misinterprets the intent of regulatory frameworks. While metrics are important, they should reflect actual risk reduction. Focusing on easily measurable but less impactful items can create a false sense of security and divert resources from critical health concerns. This is both ethically questionable and a failure to meet the spirit of regulatory requirements, which are designed to prevent serious health effects. The professional decision-making process for similar situations should involve a thorough understanding of applicable regulations, a comprehensive assessment of workplace hazards using a risk-based methodology, and the development of a program that prioritizes controls based on their effectiveness in reducing exposure and preventing illness. This includes continuous evaluation and adaptation of the program to ensure its ongoing relevance and effectiveness. Question 4. The audit findings indicate that a process involving the use of a volatile organic compound, VOC, has been identified as a significant source of airborne contaminant exposure for workers. While the facility has implemented a comprehensive training program on safe handling procedures and has provided workers with appropriate respirators, the exposure levels, though reduced, remain above the established permissible exposure limit (PEL). Based on the hierarchy of controls, which of the following represents the most appropriate and regulatory compliant course of action for the certified industrial hygienist to recommend? Option A. Recommend the procurement of higher efficiency particulate respirators to provide enhanced protection. Option B. Recommend a reduction in the amount of time workers spend in the affected area through job rotation. Option C. Recommend an increase in the frequency and duration of respiratory protection training and a review of the respirator fit testing program. Option D. Recommend the investigation and implementation of engineering controls, such as local exhaust ventilation or process enclosure, to capture or contain the VOC at its source. The correct answer is D. Recommend the investigation and implementation of engineering controls, such as local exhaust ventilation or process enclosure, to capture or contain the VOC at its source. Explanation. The audit findings indicate a potential gap in the implementation of the hierarchy of controls for a specific chemical exposure. This scenario is professionally challenging because it requires the certified industrial hygienist, C, to not only identify the deficiency, but also to prioritize and recommend the most effective and compliant control measures. The challenge lies in balancing immediate risk reduction with long-term sustainability and regulatory adherence, ensuring that the chosen controls are both technically feasible and legally defensible under U.S. OSHA regulations. The correct approach, prioritizing elimination or substitution, represents best professional practice because it directly addresses the hazard at its source, aligning with the fundamental principles of the hierarchy of controls as mandated by OSHA General Duty Clause and specific substance standards. Elimination removes the hazard entirely, and substitution replaces it with a less hazardous alternative, thereby preventing exposure without relying on worker behavior or complex systems. This proactive approach is ethically sound and legally compliant, minimizing the potential for future incidents and reducing the burden on administrative controls and PPE. An incorrect approach that focuses solely on administrative controls, or PPE, fails to adequately address the root cause of the hazard. Relying primarily on administrative controls, such as work rotation or enhanced training, is ethically problematic as it places a greater burden on the worker and may not be consistently effective in preventing exposure, especially under varying work conditions. From a regulatory standpoint, this approach is often considered a less preferred control measure by OSHA, which expects employers to implement higher-level controls when feasible. Similarly, an approach that emphasizes PPE as the primary solution is ethically questionable because it shifts the responsibility for protection onto the individual worker and is often the least effective control measure. OSHA regulations typically require PPE to be used only when engineering and administrative controls are not feasible or as a supplementary measure, not as the primary means of protection. Failure to implement higher-level controls when available constitutes a regulatory failure under OSHA standards, potentially leading to citations and increased risk of occupational illness or injury. The professional decision-making process for similar situations should involve a systematic evaluation of the hazard, followed by a thorough assessment of all feasible control options, strictly adhering to the hierarchy of controls. The CIH must consider the effectiveness, feasibility, and regulatory compliance of each control measure. This involves consulting relevant OSHA standards, industry best practices, and technical literature. The decision should always favor controls that eliminate or reduce the hazard at the source before considering controls that rely on worker behavior or personal protective equipment. Documentation of the hazard assessment and the rationale for control selection is crucial for demonstrating due diligence and compliance. Question 5. The monitoring system demonstrates intermittent readings for a specific airborne contaminant that occasionally approach and, in a few instances, slightly exceed the permissible exposure limit (PEL) established by OSHA. The sampling was conducted over a typical work shift using personal sampling pumps and appropriate sorbent tubes. Which of the following represents the most appropriate industrial hygiene response? Option A. Immediately implement enhanced engineering controls, such as local exhaust ventilation, to ensure exposures are well below the PEL, given the exceedances. Option B. Conduct a thorough investigation into the potential causes of the elevated readings, including a review of sampling methodology, process changes, and existing control effectiveness before implementing further controls. Option C. Reevaluate the PEL for the contaminant, as the current limit may be overly stringent based on the observed intermittent exceedances. Option D. Disregard the intermittent exceedances as likely due to sampling variability or transient process fluctuations, and continue routine monitoring. Correct answer is B. Conduct a thorough investigation into the potential causes of the elevated readings, including a review of sampling methodology, process changes, and existing control effectiveness, before implementing further controls. Explanation. This scenario presents a common challenge in industrial hygiene, interpreting and acting upon air monitoring data that may not perfectly align with established exposure limits or initial assumptions. The professional challenge lies in discerning the true significance of the findings, considering potential sources of error, and determining the most appropriate course of action to protect worker health, all while adhering to regulatory requirements. This requires a nuanced understanding of sampling methodologies, statistical interpretation, and the hierarchy of controls. The correct approach represents best professional practice because it prioritizes a comprehensive and systematic evaluation of the monitoring results. It acknowledges that a single exceedance or a pattern of results close to the limit warrants further investigation rather than immediate, potentially unnecessary, or insufficient interventions. This approach aligns with the principles of good industrial hygiene practice, which emphasize proactive risk assessment and management. Specifically, it adheres to the spirit and intent of OSHA Air Contaminant Standard 29 CFR 1910, which requires employers to assess employee exposure and implement controls when exposures exceed permissible exposure limits, PEL, or when there is a potential for overexposure. The emphasis on investigating the cause of the elevated readings, considering sampling variability, and evaluating the effectiveness of existing controls is a direct application of the employer's General Duty Clause, Section 5(a)(1) of the OSH Act, to provide a workplace free from recognized hazards. An incorrect approach that immediately implements engineering controls without further investigation fails to consider the potential for sampling error or transient conditions. This can lead to unnecessary costs and may not address the root cause if the elevated readings were due to an anomaly. Ethically, it might be seen as overreacting without sufficient data. Another incorrect approach that dismisses the elevated readings without a thorough review of the sampling methodology and potential confounding factors is a significant regulatory and ethical failure. This could violate the employer's obligation to monitor and control exposures, potentially leading to continued overexposure and health risks for employees. It demonstrates a lack of due diligence and a disregard for the principles of occupational health and safety. The professional decision-making process for similar situations should involve a structured approach. 1. Review the monitoring data in the context of established exposure limits and the specific work processes. 2. Critically evaluate the sampling methodology, including equipment calibration, sampling duration, placement, and potential interferences. 3. Consider the variability inherent in air sampling and whether the observed levels are statistically significant. 4. Investigate potential sources of the contaminant, including process changes, equipment malfunctions, or changes in work practices. 5. Assess the effectiveness of existing controls. 6. Based on the comprehensive evaluation, determine the appropriate course of action, which may include further monitoring, implementation or modification of controls, or no immediate action if the data indicates no significant risk. 7. Document all findings, decisions, and actions taken. Question 6. Process analysis reveals that an industrial hygienist has conducted an exposure assessment for a client and found that airborne concentrations of a specific chemical exceed the ECG threshold limit value (TLV) and the AHA workplace environmental exposure level (WEL). The client, concerned about the cost of implementing engineering controls, requests that the hygienist reevaluate the data or interpret the results in a way that suggests the exposures are not a significant concern, implying that future business may depend on a favorable report. What is the most ethically and professionally sound approach for the industrial hygienist? Option A. Present the findings objectively, clearly stating the exceedances of the ECG TLV and AHA WEL, explaining the potential health risks associated with these exposures, and recommending appropriate control measures based on these established guidelines. Option B. Inform the client that the data is inconclusive and requires further, unspecified testing, thereby delaying a definitive report and avoiding immediate confrontation over the exceedances. Option C. Agree to omit any mention of the exceedances from the final report and focus solely on other, less concerning aspects of the workplace environment to avoid conflict with the client. Option D. Adjust the interpretation of the data to minimize the significance of the exceedances, focusing on less critical aspects of the assessment to satisfy the client's request for a favorable report. The correct answer is A. Present the findings objectively, clearly stating the exceedances of the ECG TLV and AHA WEL, explaining the potential health risks associated with these exposures, and recommending appropriate control measures based on these established guidelines. Explanation. Scenario analysis. This scenario presents a common ethical dilemma in industrial hygiene, where a consultant faces pressure to align findings with a client's desired outcome, potentially compromising the integrity of their professional judgment and the application of established standards. The challenge lies in balancing the client's expectations and business interests with the paramount duty to protect worker health and safety based on scientific evidence and recognized guidelines. The consultant must navigate the potential for financial repercussions, loss of future work, against their ethical obligations and professional standards. Correct approach analysis. The correct approach involves steadfastly adhering to the ECG threshold limit values, TLV, and the AHA workplace environmental exposure levels, WEEL, as the authoritative benchmarks for assessing exposure. This upholds the professional's commitment to using the most current, scientifically validated guidance for evaluating occupational health risks. By presenting the data objectively and explaining the implications of exceeding these limits, the consultant fulfills their ethical duty to inform the client accurately and recommend appropriate control measures, prioritizing worker safety above all else. This aligns with the core principles of industrial hygiene practice, which emphasize unbiased assessment and risk management. Incorrect approaches analysis. One incorrect approach involves selectively presenting data or downplaying exceedances to satisfy the client's request. This is a direct violation of professional ethics and the principles of unbiased scientific assessment. It misrepresents the actual risk to workers and can lead to inadequate or non-existent controls, exposing employees to potential health hazards. This approach undermines the credibility of the industrial hygienist and the profession. Another incorrect approach is to immediately concede to the client's demand to alter the interpretation of the data without a scientifically sound basis. This demonstrates a lack of professional integrity and a failure to apply established standards. It suggests that the consultant's judgment is subordinate to the client's wishes, rather than being guided by objective scientific evidence and recognized guidelines like GTLVs and AHA WEEL. This can lead to a false sense of security for the client and continued exposure for workers. A further incorrect approach is to avoid presenting any findings that might be unfavorable to the client, effectively withholding critical information. This is a breach of the consultant's duty to provide a comprehensive and accurate assessment. The purpose of an industrial hygiene assessment is to identify and evaluate hazards, and failing to report significant findings, even if they are inconvenient, is professionally irresponsible and ethically unsound. Professional reasoning. Professionals should approach such situations by first understanding the client's concerns and objectives. However, this understanding must be framed within the context of their professional responsibilities. The decision-making process should involve 1. Clearly identifying the relevant professional standards and guidelines, e.g., GTLV AHA WEEL. 2. Objectively collecting and analyzing all relevant data. 3. Interpreting the data strictly in accordance with these established standards. 4. Communicating findings clearly and factually to the client, explaining the implications of any exceedances. 5. Recommending appropriate, evidence-based control strategies. 6. If the client pushes back, reiterating the scientific basis for the findings and the importance of adhering to recognized guidelines for worker protection, while maintaining professional boundaries and ethical obligations. Question 7. Quality control measures reveal a cluster of employees in a manufacturing facility reporting symptoms such as headaches, dizziness, fatigue, and occasional shortness of breath. These symptoms are not immediately attributable to a single known process upset or acute event. The facility manufactures a variety of plastic components, utilizing several chemical agents in its processes. As the certified industrial hygienist, what is the most appropriate initial step to systematically investigate potential target organ toxicity affecting the respiratory, nervous, and cardiovascular systems? Option A. Immediately inform management that the symptoms are likely due to stress and recommend employee wellness programs without further investigation into workplace exposures. Option B. Focus solely on investigating the most recently introduced chemical in the manufacturing process, assuming it is the sole cause of the reported symptoms. Option C. Conduct a comprehensive walkthrough survey to identify all potential chemical and physical hazards, review existing exposure data, and initiate targeted air monitoring for suspected agents based on the observed symptoms and known processes. Option D. Advise employees to report any symptoms to their personal physicians and await individual medical diagnoses before initiating any workplace investigation. The correct answer is C. Conduct a comprehensive walkthrough survey to identify all potential chemical and physical hazards, review existing exposure data, and initiate targeted air monitoring for suspected agents based on the observed symptoms and known processes. Explanation. Scenario analysis. This scenario presents a challenge because the observed symptoms are nonspecific and could be attributed to various causes, including occupational exposures, lifestyle factors, or pre-existing conditions. Differentiating between these requires a systematic and evidence-based approach, adhering strictly to the established regulatory framework for industrial hygiene in the United States. The certified industrial hygienist, C, must avoid premature conclusions and ensure all investigations are grounded in recognized scientific principles and regulatory compliance. Correct approach analysis. The correct approach involves a comprehensive investigation that begins with a thorough review of the available data, including the quality control measures, employee health records, with appropriate consent and privacy considerations, and existing exposure assessments. This is followed by a detailed walkthrough survey to identify potential hazards, specifically focusing on the target organ systems mentioned. The investigation must then involve appropriate exposure monitoring, considering the specific chemicals or physical agents suspected based on the work processes and observed symptoms. This systematic process aligns with the principles outlined in OSHA standards, e.g. 29 CFR 1910 Subpart Z toxic and hazardous substances, and the AHA guidance on exposure assessment and control. The goal is to establish a causal link between workplace exposures and the observed health effects, which is a fundamental requirement for effective industrial hygiene practice and regulatory compliance. Incorrect approaches analysis. One incorrect approach would be to immediately attribute the symptoms solely to a single, highly publicized chemical without conducting a thorough investigation. This fails to consider other potential workplace hazards or non-occupational causes, violating the principle of objective assessment and potentially leading to misallocation of resources and ineffective control strategies. It also bypasses the requirement for data-driven conclusions mandated by regulatory bodies like OSHA. Another incorrect approach would be to dismiss the reported symptoms as psychosomatic or unrelated to work without any objective investigation. This demonstrates a failure to uphold the ethical responsibility to protect worker health and safety and ignores the potential for occupational causation, which is a core tenet of industrial hygiene practice. Such an approach could also lead to regulatory violations if a genuine occupational hazard is present and unaddressed. A third incorrect approach would be to rely solely on anecdotal evidence or employee suggestions about the cause of the symptoms without conducting scientifically sound exposure assessments. While employee input is valuable, it cannot replace the need for objective data collection and analysis to confirm or refute potential causal relationships, as required by regulatory standards and professional best practices. Professional reasoning. Professionals should employ a structured decision-making framework that begins with problem identification and data gathering. This is followed by hazard identification, exposure assessment, risk characterization, and the development and implementation of control measures. Throughout this process, adherence to relevant U.S. regulations, e.g., OSHA, NIOSH guidelines, and professional standards, e.g., AHA, is paramount. The CIH must maintain objectivity, critically evaluate all data, and communicate findings clearly and ethically. Question 8. The monitoring system demonstrates a measured airborne concentration of a regulated substance at 0.8 times the established permissible exposure limit, PEL. The laboratory report indicates that the analytical method used has a limit of detection LOD of 0.5 times the PEL. Which of the following interpretations and subsequent actions best aligns with regulatory requirements and professional practice for ensuring worker protection? Option A. Immediately implement enhanced engineering controls and require respiratory protection for all workers in the area, as the measured concentration is close to the PEL and the LOD is also relatively high. Option B. Conclude that worker exposure is below the PEL, as the measured concentration is less than the PEL, and no further action is immediately required beyond routine monitoring. Option C. Recognize that, while the measured concentration is below the PEL, the analytical method's LOD is also below the PEL, indicating a potential for exposures to exist at levels between the LOD and the measured concentration that could still approach or exceed the PEL, necessitating a review of sampling strategy and potential for more sensitive analytical methods or enhanced controls. Option D. Declare that the substance is not present at a level of concern because the measured concentration is below the LOD of the analytical method. The correct answer is B. Conclude that worker exposure is below the PEL, as the measured concentration is less than the PEL, and no further action is immediately required beyond routine monitoring. Explanation. This scenario presents a common challenge in industrial hygiene. Interpreting laboratory results in the context of established occupational exposure limits OL, and understanding the implications for worker protection. The difficulty lies not just in comparing a numerical value to a limit, but in considering the nuances of sampling methodology, analytical variability, and the specific regulatory framework governing the workplace. A thorough understanding of the OEL's basis, the limitations of the analytical method, and the potential for exposure variability is crucial for making sound professional judgments. The correct approach represents best professional practice because it integrates multiple facets of industrial hygiene principles and regulatory compliance. It acknowledges that a single sample result is a snapshot and must be interpreted within the broader context of the OEL, which is itself based on scientific evidence and intended to protect worker health. This approach prioritizes worker safety by considering the potential for exceeding the OEL and the need for further investigation or control measures, aligning with the fundamental ethical and regulatory duty of an industrial hygienist to prevent occupational illness and injury. This aligns with the principles of hazard identification, risk assessment, and control mandated by regulations such as OSHA General Duty Clause and specific substance standards. An incorrect approach that solely focuses on the numerical comparison without considering the analytical method's limitations fails to account for potential measurement error. This can lead to either overregulation, implementing controls when not truly necessary, or underregulation, failing to act when exposure is indeed problematic. Ethically, this is a failure to exercise due diligence. Another incorrect approach that ignores the OEL and focuses only on the analytical detection limit is problematic because the detection limit is not synonymous with a health-based exposure limit. It may indicate the absence of detectable levels by a specific method, but it does not confirm the absence of a health risk if the OEL is higher than the detection limit. This approach risks overlooking exposures that, while below the detection limit, could still be significant from a health perspective if they approach or exceed the OEL. Regulatory failure occurs because the OEL is the benchmark for compliance and worker protection. Professionals should approach such situations by first understanding the specific OEL applicable to the substance and the work environment, including its basis and any associated guidance. Second, they must understand the analytical method used, including its sensitivity, specificity, and potential sources of error. Third, they should consider the sampling strategy and its representativeness of actual worker exposure. Finally, they must integrate these factors to determine if the exposure poses a risk, and if further action, such as additional monitoring, engineering controls, administrative controls, or personal protective equipment, is warranted, always in compliance with applicable regulations. Question 9. Process analysis reveals a newly implemented chemical synthesis operation involving novel reagents and reaction conditions. While no specific occupational exposure limits OL are established for the primary reactants or anticipated byproducts, the process involves elevated temperatures and pressures. Which of the following represents the most appropriate initial industrial hygiene approach to ensure worker safety? Option A. Rely on the absence of established OELs as an indication that significant exposure risks are unlikely and monitor worker health for any emergent symptoms. Option B. Focus solely on engineering controls that isolate the process, assuming that complete containment will eliminate all potential exposure pathways. Option C. Conduct a comprehensive risk assessment that prioritizes hazard anticipation and recognition, followed by a qualitative, and where necessary, quantitative evaluation of potential exposures, and the implementation of controls based on the hierarchy of controls. Option D. Implement generic personal protective equipment, PPE, such as respirators and gloves based on the general chemical nature of the reagents, without a detailed exposure assessment. The correct answer is C. Conduct a comprehensive risk assessment that prioritizes hazard anticipation and recognition, followed by a qualitative, and, where necessary, quantitative evaluation of potential exposures, and the implementation of controls based on the hierarchy of controls. Explanation. Scenario analysis. This scenario presents a common challenge in industrial hygiene, where a new process introduces potential hazards that are not immediately obvious or well documented. The professional must move beyond simply identifying known risks to proactively anticipating and evaluating novel exposures. The challenge lies in the absence of established exposure limits or historical data, requiring a robust risk assessment methodology that can adapt to uncertainty and incomplete information. Correct approach analysis. The correct approach, focusing on a comprehensive risk assessment that integrates anticipation, recognition, evaluation, and control, represents best professional practice because it aligns with the fundamental principles of industrial hygiene as outlined by regulatory bodies such as OSHA, Occupational Safety and Health Administration. In the United States, OSHA General Duty Clause, Section 5(a)(1) of the OSH Act mandates employers provide a workplace free from recognized hazards. A proactive risk assessment is the mechanism by which recognized hazards are identified and controlled. This approach systematically addresses the life cycle of a hazard, from its conceptualization to its mitigation, ensuring that potential exposures are considered before they manifest as health issues. It emphasizes a thorough understanding of the process, potential exposure pathways, and the inherent properties of the materials involved, leading to the selection of appropriate control measures based on the hierarchy of controls. Incorrect approaches analysis. One incorrect approach would be to rely solely on existing permissible exposure limits, PEL, for known substances, ignoring the potential for novel chemical reactions or byproducts. This fails to address the anticipation and recognition phases effectively, as it assumes all hazards are already cataloged and regulated. Ethically and regulatorily, this is a failure to proactively identify and control recognized hazards, which includes those that are reasonably foreseeable even if not explicitly listed. Another incorrect approach would be to implement controls based on anecdotal evidence or worker complaints without a systematic evaluation. While worker feedback is valuable, it often represents a point where exposure has already occurred or is significant. This approach bypasses the crucial evaluation phase, which requires objective data collection and analysis to quantify exposure levels and assess risk accurately. Regulatorily, this is insufficient as it does not demonstrate a systematic effort to understand and control hazards before they cause harm. A third incorrect approach would be to defer action until a specific health outcome or incident occurs. This reactive stance is contrary to the preventative nature of industrial hygiene. It represents a significant ethical failure to protect worker health and a regulatory violation, as employers have a duty to prevent hazards, not just respond to them after damage has been done. Professional reasoning. When faced with a new process, a professional industrial hygienist should employ a structured risk assessment framework. This begins with a thorough understanding of the process inputs, operations, and outputs. Next, potential hazards are anticipated based on the chemistry, physics, and toxicology of the materials and processes. This is followed by recognition of specific exposure scenarios and pathways. Evaluation involves qualitative and quantitative assessment of exposure levels, considering factors like frequency, duration, and intensity. Finally, control measures are selected and implemented based on the hierarchy of controls: elimination, substitution, engineering controls, administrative controls, and personal protective equipment, with a plan for ongoing monitoring and reevaluation. This systematic, proactive approach ensures compliance with regulatory requirements and upholds the ethical obligation to protect worker health. Question 10. Market research demonstrates that a manufacturing facility producing fine powders is experiencing increased worker complaints related to respiratory irritation. The facility's current industrial hygiene program primarily relies on total dust sampling and gravimetric analysis to assess airborne particulate exposures against OSHA PELs. To optimize the sampling strategy and ensure comprehensive worker protection, which of the following approaches best aligns with regulatory requirements and best professional practice for assessing potential health risks associated with these particulates? Option A. Implement a comprehensive air monitoring program using only real-time particle counters to provide immediate feedback on general particulate levels, without subsequent laboratory analysis. Option B. Increase the frequency of total dust gravimetric sampling and rely solely on these results to demonstrate compliance with OSHA PELs, assuming all significant exposures are captured. Option C. Supplement total dust gravimetric analysis with sampling methods that incorporate particle size fractionation, e.g., using cyclones or impactors, and, where appropriate, microscopy to characterize particle morphology, especially for respirable fractions. Option D. Discontinue gravimetric analysis and exclusively utilize advanced microscopy techniques to identify and quantify all airborne particles, focusing on their visual characteristics. The correct answer is C. Supplement total dust gravimetric analysis with sampling methods that incorporate particle size fractionation, e.g., using cyclones or impactors, and, where appropriate, microscopy to characterize particle morphology, especially for respirable fractions. Explanation. This scenario presents a common challenge in industrial hygiene, optimizing sampling strategies for particulate matter to ensure compliance with regulatory standards while managing resources effectively. The core difficulty lies in balancing the need for accurate gravimetric analysis, which measures total mass, with the requirement to understand particle size distribution and morphology, which are critical for assessing health impacts and selecting appropriate controls. A purely gravimetric approach might miss significant exposures to respirable particles, while an overly complex particle size analysis without a clear regulatory driver could be inefficient. Correct approach prioritizes understanding the specific regulatory requirements for particulate sampling and analysis. In the U.S., this would involve adhering to OSHA standards, e.g., 29 CFR 1910 Subpart Z, and NIOSH methods. Best professional practice dictates a tiered approach. First, conduct gravimetric analysis to determine total airborne concentration against established permissible exposure limits (PEL). Concurrently, if the nature of the hazard or the process suggests that particle size is a critical factor, e.g., potential for respiratory deposition of fine particles, then employ methods for particle size characterization, such as using impactors or cyclones in conjunction with gravimetric analysis, or microscopy for morphological identification. This integrated strategy ensures that both the quantity and the relevant characteristics of the particulate exposure are assessed, allowing for informed risk assessment and control selection, aligning with the principles of good industrial hygiene practice and regulatory compliance. An incorrect approach would be to solely rely on gravimetric analysis without considering particle size when the process generates fine or ultrafine particles known to be respirable and potentially hazardous. This fails to adequately assess the risk of lung deposition and systemic absorption, potentially leading to underestimation of health hazards and noncompliance with the spirit, if not the letter, of regulations that aim to protect worker health from all significant airborne contaminants. Another incorrect approach would be to immediately opt for highly sophisticated and resource-intensive particle size analysis and microscopy for every sampling event, regardless of the known hazards or regulatory triggers. This represents poor resource management and an inefficient application of industrial hygiene principles, deviating from the ethical obligation to use resources judiciously while still achieving the primary goal of worker protection. It also fails to recognize that gravimetric analysis is often the primary regulatory metric. Professional decision-making in such situations requires a systematic process. 1. Identify the specific regulatory standards applicable to the workplace and the suspected contaminants. 2. Understand the physical and chemical properties of the materials being handled and the processes involved, paying particular attention to particle generation mechanisms and potential health effects related to particle size. 3. Select sampling and analytical methods that directly address the regulatory requirements and provide the necessary information for risk assessment. 4. Evaluate the cost-effectiveness and feasibility of different approaches, prioritizing those that offer the most relevant data for protecting worker health and ensuring compliance. Question 11. Assessment of a chemical's potential health effects for a new process requires an industrial hygienist to quickly gather relevant toxicological data. The hygienist has access to several potential information sources, which approach best upholds professional ethical obligations and regulatory compliance in the United States. Option A. Prioritize consulting authoritative, peer-reviewed toxicological databases and resources recognized by OSHA and NIOSH, such as the NIOSH Pocket Guide and ATSTR toxicological profiles. Option B. Utilize proprietary software or internal company databases without independently verifying the currency and comprehensiveness of their underlying data. Option C. Base the assessment on the personal experience and recollection of a senior colleague who has worked in the industry for many years. Option D. Rely primarily on informal online forums and anecdotal reports from other workers who claim to have encountered similar chemicals. The correct answer is A. Prioritize consulting authoritative, peer-reviewed toxicological databases and resources recognized by OSHA and NIOSH, such as the NIOSH Pocket Guide and ATSTR toxicological profiles. Explanation. Scenario analysis. This scenario presents an ethical dilemma for an industrial hygienist tasked with assessing potential health risks. The challenge lies in balancing the need for timely information with the limitations of readily available, potentially incomplete, or outdated toxicological data. The hygienist must navigate the ethical obligation to protect worker health while adhering to professional standards and regulatory requirements, which often necessitate the use of validated and reliable resources. The pressure to provide an immediate assessment, coupled with the potential for conflicting information from different sources, demands careful judgment and a systematic approach to data evaluation. Correct approach analysis. The correct approach involves prioritizing the use of authoritative, peer-reviewed toxicological databases and resources that are recognized by regulatory bodies like OSHA, Occupational Safety and Health Administration, and NIOSH, National Institute for Occupational Safety and Health, in the U.S. These resources, such as the NIOSH Pocket Guide to Chemical Hazards, the Agency for Toxic Substances and Disease Registry, ATSTR, toxicological profiles, and peer-reviewed scientific literature indexed in reputable databases like PubMed, provide scientifically sound information on chemical hazards, exposure limits, and health effects. Their use aligns with the ethical duty of care and the regulatory requirement to base risk assessments on credible scientific evidence. This approach ensures that decisions regarding worker protection are informed by the most reliable and up-to-date information available, minimizing the risk of under- or overprotection. Incorrect approaches analysis. Relying solely on anecdotal evidence or informal online forums, even if they appear to offer quick answers, represents a significant ethical and regulatory failure. Such sources often lack scientific rigor, are not peer-reviewed, and may contain misinformation or biased opinions. This approach violates the professional standard of using validated data and could lead to inaccurate risk assessments, potentially exposing workers to unacceptable hazards or unnecessarily disrupting operations. Using proprietary software or internal company databases without verifying their underlying data sources or ensuring they are current and comprehensive is also problematic. While these tools can be efficient, their reliability depends entirely on the quality and recency of the data they contain. If the data is outdated, incomplete, or based on flawed methodologies, the resulting assessment will be compromised. This failure to independently verify critical information can lead to noncompliance with regulatory requirements for hazard communication and exposure control. Consulting with a colleague who has experience with a similar chemical without referencing established toxicological data is another ethically questionable approach. While collegial consultation is valuable, it should supplement, not replace, the rigorous review of scientific literature and authoritative databases. Personal experience, while informative, can be subjective and may not encompass the full spectrum of potential health effects or the nuances of current scientific understanding. This approach risks perpetuating outdated knowledge or overlooking critical safety information. Professional reasoning. When faced with a need to assess toxicological information, industrial hygienists should follow a structured decision-making process. This begins with identifying the specific chemical or hazard in question. Next, they should consult authoritative sources, prioritizing those recognized by regulatory agencies. This includes official government databases, peer-reviewed scientific literature, and established toxicological reference materials. If initial searches yield insufficient or conflicting information, the hygienist should broaden their search to include other reputable sources, critically evaluating the methodology and credibility of each. The goal is to synthesize information from multiple reliable sources to form a comprehensive and scientifically defensible risk assessment. Ethical considerations, such as the duty to protect worker health and the obligation to maintain professional competence should guide every step of this process. Question 12. Comparative studies suggest that a novel industrial chemical exhibits moderate dermal absorption in animal models, but its metabolic pathways in humans are largely unknown, with some in vitro data hinting at the potential for bioactivation into more reactive intermediates. Given this limited but suggestive toxicokinetic information, what is the most ethically and professionally sound approach for an industrial hygienist to recommend regarding worker protection during initial handling and processing? Option A. Advise workers to avoid direct skin contact and ensure good general ventilation, as the dermal absorption is only moderate and the metabolic data is inconclusive. Option B. Prohibit the use of the chemical until comprehensive human toxicokinetic studies are completed, which could take several years. Option C. Recommend enhanced personal protective equipment, PPE, with a focus on impermeable materials for skin and respiratory protection, and implement local exhaust ventilation, LEV, at points of potential exposure, pending further toxicokinetic studies. Option D. Rely solely on the animal model data for dermal absorption and assume human metabolism will follow similar, non-toxic pathways, thus requiring only standard PPE. The correct answer is C. Recommend enhanced personal protective equipment, PPE, with a focus on impermeable materials for skin and respiratory protection, and implement local exhaust ventilation, LEV, at points of potential exposure, pending further toxicokinetic studies. Explanation. Scenario analysis. This scenario presents a professional challenge because an industrial hygienist must balance the immediate need for worker protection with the scientific uncertainty surrounding the toxicokinetic profile of a novel chemical. The ethical dilemma arises from the potential for harm if the chemical is more readily absorbed or metabolized into more toxic intermediates than initially assumed, versus the potential for unnecessary alarm or costly control measures if the initial assumptions are overly conservative. The industrial hygienist must exercise sound professional judgment, relying on available data and established principles of toxicology and industrial hygiene practice, while acknowledging the limitations of current knowledge. Correct approach analysis. The correct approach involves a precautionary principle, informed by the available toxicokinetic data, and a conservative interpretation of potential risks. This aligns with the ethical obligation to protect worker health and safety, as mandated by regulatory frameworks such as OSHA General Duty Clause, 29 CFR 1910, 141, which requires employers to provide a workplace free from recognized hazards by recommending enhanced personal protective equipment, PPE, and implementing engineering controls based on the potential for significant absorption and metabolism. The industrial hygienist is proactively mitigating risk. This approach prioritizes worker well-being in the face of uncertainty, which is a cornerstone of professional industrial hygiene practice and ethical conduct. It also reflects the hierarchy of controls, emphasizing engineering solutions where feasible. Incorrect approaches analysis. One incorrect approach would be to dismiss the need for enhanced controls solely because the initial toxicokinetic data is incomplete or suggests a lower risk. This fails to acknowledge the inherent uncertainties in toxicological assessments, particularly for novel substances. Ethically, this approach prioritizes economic considerations or convenience over worker safety, violating the fundamental duty of care. From a regulatory standpoint, it could be seen as a failure to identify and abate recognized hazards, potentially contravening OSHA standards. Another incorrect approach would be to implement overly stringent and potentially unnecessary controls without a clear scientific rationale beyond speculative worst-case scenarios. While caution is warranted, excessive controls can lead to significant economic burden, worker resistance, and a dilution of focus on more critical hazards. This approach may not be supported by the available data and could be challenged as not being based on a sound risk assessment, which is a requirement for effective hazard management under regulatory frameworks. A third incorrect approach would be to delay any protective measures until definitive, long-term toxicokinetic studies are completed. This is ethically unacceptable, as it exposes workers to potential harm during the period of investigation. Regulatory frameworks like OSHA emphasize prompt action to address known or suspected hazards. Waiting for complete data in this context would be a dereliction of duty and a failure to act in a timely manner to protect worker health. Professional reasoning. Professionals should approach such dilemmas by first thoroughly reviewing all available data, including any preliminary toxicokinetic studies, even if incomplete. They should then consult relevant toxicological databases and literature for similar compounds. The next step is to apply established principles of industrial hygiene and toxicology, such as the hierarchy of controls, and to adopt a precautionary approach when significant uncertainty exists regarding potential health effects. This involves a risk assessment that considers both the likelihood and severity of potential harm, communication with management and workers about the uncertainties, and the rationale for recommended controls is crucial. The decision-making process should be documented, justifying the chosen course of action based on the available evidence and professional judgment, always prioritizing worker safety. Question 13. Compliance review shows that a manufacturing facility has conducted a comprehensive risk assessment for its chemical handling processes 5 years ago. Since then, the company has introduced a new automated dispensing system, modified its ventilation controls in 2 production areas, and experienced a turnover of 40% of its production staff. The current risk assessment documentation has not been updated to reflect these changes. What is the most appropriate course of action for the certified industrial hygienist? Option A. Suggests that the new automated dispensing system be assessed independently, but the overall risk assessment can remain unchanged as it was thorough at the time of its creation. Option B. Recommend a review of the risk assessment only for the areas where ventilation controls were modified, assuming other aspects are still adequately covered. Option C. Initiate a full re-evaluation of the risk assessment for all chemical handling processes, incorporating the new dispensing system, ventilation modifications, and considering the impact of staff turnover on work practices and training. Option D. Advise management that since no specific health complaints have been reported, the existing risk assessment remains sufficient until a major incident occurs. Correct answer is C. Initiate a full re-evaluation of the risk assessment for all chemical handling processes, incorporating the new dispensing system, ventilation modifications, and considering the impact of staff turnover on work practices and training. Explanation. Scenario analysis. This scenario presents a common challenge in industrial hygiene, balancing the need for effective risk management with resource constraints and evolving operational demands. The challenge lies in the potential for complacency after initial assessments, the difficulty in quantifying the impact of subtle changes in work practices, and the ethical imperative to protect worker health even when immediate, severe hazards are not apparent. A professional industrial hygienist must exercise sound judgment to ensure that risk assessments remain relevant and that control measures are adequately maintained and adapted. Correct approach analysis. The correct approach involves a proactive and systematic review of existing risk assessments and control measures. This aligns with the fundamental principles of industrial hygiene and regulatory requirements, e.g., OSHA General Duty Clause, specific substance standards, and hazard communication regulations in the U.S. Best professional practice dictates that risk assessments are not static documents but living tools that require periodic re-evaluation. This includes considering changes in processes, materials, equipment, work practices, and the emergence of new scientific information regarding health effects. The systematic review ensures that all identified hazards are re-evaluated for their current risk level and that control measures remain effective and appropriate, thereby fulfilling the ethical obligation to protect worker health and safety and the legal obligation to comply with applicable standards. Incorrect approaches analysis. One incorrect approach involves relying solely on the initial risk assessment without considering recent operational changes. This is a regulatory failure because it implies a lack of due diligence in ensuring ongoing compliance with hazard identification and control requirements. Ethically, it risks exposing workers to previously unrecognized or inadequately controlled hazards. Another incorrect approach is to only re-evaluate when a specific incident occurs. This reactive stance is a significant professional and regulatory failure. Regulations and ethical standards mandate a proactive approach to hazard identification and control, not a wait-and-see approach that prioritizes response over prevention. Relying on incidents to trigger re-evaluation means that workers may have been exposed to unacceptable risks for an extended period. A third incorrect approach is to assume that the absence of reported health complaints equates to effective control. While worker feedback is valuable, It is not a substitute for a comprehensive risk assessment. Many occupational illnesses have long latency periods, and workers may not associate subtle symptoms with workplace exposures. This approach fails to meet the regulatory requirement for a systematic evaluation of hazards and risks and represents an ethical lapse in safeguarding worker well-being. Professional reasoning. Professionals should adopt a cyclical risk management process. This involves initial hazard identification and risk assessment, followed by the implementation of control measures. Crucially, this cycle must include regular monitoring, review, and reevaluation. The trigger for reevaluation should be a combination of scheduled reviews, e.g., annually or biannually, significant changes in operations, new scientific information, or the occurrence of incidents or near misses. This systematic, proactive approach ensures that risk assessments remain current and that control strategies are effective in protecting worker health, thereby upholding professional standards and regulatory compliance. Question 14. To address the challenge of assessing potential hearing loss risk from a noisy industrial environment, a certified industrial hygienist is reviewing acoustic data. The data includes measurements of sound pressure levels across various frequencies. Which of the following understandings of acoustic principles is most critical for accurately evaluating the hazard and determining appropriate control measures? Option A. The direct proportionality between sound pressure level and the perceived loudness of a sound, irrespective of its frequency content. Option B. The inverse relationship between frequency and wavelength, and how this impacts sound propagation in different media. Option C. The concept of sound intensity being solely determined by the amplitude of the sound wave, without regard to its temporal characteristics. Option D. The varying sensitivity of the human ear to different frequencies, and how this influences the potential for noise-induced hearing loss at specific sound pressure levels. The correct answer is B. The inverse relationship between frequency and wavelength, and how this impacts sound propagation in different media. Explanation. Scenario analysis. This scenario presents a common challenge in industrial hygiene, interpreting acoustic data to assess potential hearing loss risk. The difficulty lies in understanding the fundamental relationships between sound pressure, frequency, and wavelength, and how these relate to the human auditory system sensitivity and the regulatory limits for occupational noise exposure. A hygienist must move beyond simply reading decibel levels to comprehending the acoustic characteristics that contribute to hazardous noise. Correct approach analysis. The correct approach involves recognizing that while sound pressure level, SPL, is a primary metric for noise intensity, the frequency content of the sound is crucial for determining its potential to cause hearing damage. The human ear is not equally sensitive to all frequencies. It is most sensitive to mid-range frequencies, around 1000-4000 Hz. Wavelength, while related to frequency and the speed of sound, is less directly used in standard occupational noise exposure assessments compared to frequency and sound pressure. Therefore, understanding how different frequencies contribute to the overall sound exposure and how this relates to established permissible exposure limits, PEL, or action levels, is paramount. This aligns with the principles of industrial hygiene as outlined in regulations like OSHA Occupational Noise Exposure Standard, 29 CFR 1910-95, which specifies frequency-weighted sound levels, e.g., dBA, and time-weighted averages to protect workers from hearing impairment. Incorrect approach is analysis. Focusing solely on sound pressure level without considering frequency is an incomplete assessment. This fails to account for the varying sensitivity of the human ear at different frequencies. Noise at a lower frequency with a high SPL might be perceived as less intense than a noise at a mid-range frequency with a lower SPL, yet the latter could pose a greater risk of hearing damage. This approach would violate the spirit and intent of noise regulations, which are designed to protect against hearing loss across the spectrum of human hearing. Considering only wavelength is also an incorrect approach for direct risk assessment in industrial hygiene. A wavelength is a fundamental property of sound waves and is inversely proportional to frequency. Wavelength equals speed of sound/frequency. It is not the primary parameter used in setting occupational noise exposure limits. Regulations are based on sound pressure levels, often frequency-weighted, like dBA, which directly correlate to perceived loudness and potential for damage. Relying on wavelength alone would lead to a misinterpretation of the acoustic hazard. Ignoring the relationship between sound pressure and frequency would lead to an inadequate understanding of the noise hazard. It is the combination of intensity, sound pressure, and the specific frequencies present that determines the overall risk to hearing. Without this integrated understanding, a hygienist cannot accurately assess exposure or recommend appropriate controls. This would be a failure to apply fundamental principles of acoustics in the context of occupational health and safety, potentially leading to non-compliance with regulatory requirements. Professional reasoning. Professionals should employ a systematic approach to acoustic hazard assessment. This begins with identifying potential noise sources and conducting noise surveys using calibrated sound level meters. The data collected should include not only overall sound pressure levels, but also frequency analysis, e.g., octave band or one-third octave band analysis. This detailed information allows for the calculation of frequency-weighted exposure levels, e.g., D/3, and comparison against regulatory limits. Understanding the acoustic properties of the noise, including its frequency spectrum, is essential for selecting appropriate hearing protection devices, HPD, and implementing effective engineering or administrative controls. The decision-making process should always prioritize worker protection and compliance with applicable standards, such as those set by OSHA. Question 15. The performance metrics show an increase in reported respiratory illnesses among employees working in the research and development wing, with preliminary investigations suggesting potential exposure to airborne fungal spores from a compromised HVAC system. Which of the following approaches best represents a comprehensive and compliant strategy for managing this biological hazard? Option A. Implement a robust personal respiratory protection program, including fit testing and training on the proper use of N95 respirators for all personnel working in the affected wing. Option B. Conduct a thorough risk assessment to identify the specific fungal species and their concentration, followed by the implementation of engineering controls such as HEPA filtration and containment of the compromised HVAC components, supplemented by administrative controls like restricted access and enhanced cleaning protocols. Option C. Increase the frequency of general housekeeping and disinfection procedures throughout the entire facility to mitigate any potential widespread contamination. Option D. Immediately shut down the HVAC system in the affected wing and mandate remote work for all employees until the system can be fully replaced. Correct answer is A. Implement a robust personal respiratory protection program, including fit testing and training on the proper use of N95 respirators for all personnel working in the affected wing. Explanation. Scenario analysis. This scenario presents a challenge in industrial hygiene by requiring the evaluation of different approaches to managing biological hazards in a workplace. The core difficulty lies in selecting the most effective and compliant strategy among several plausible options, each with potential benefits and drawbacks. The industrial hygienist must not only understand the nature of biological agents, but also apply regulatory knowledge and best practices to protect worker health. The performance metrics, while indicating a need for action, do not dictate the specific solution, necessitating professional judgment. Correct approach analysis. The correct approach emphasizes a multifaceted strategy that prioritizes elimination and substitution where feasible, followed by engineering controls, administrative controls, and finally, personal protective equipment, PPE. This hierarchy of controls is a cornerstone of industrial hygiene practice and is mandated by regulatory frameworks such as OSHA General Duty Clause 29 U.S.C. Section 654, A1, which requires employers to provide a workplace free from recognized hazards. Specifically, for biological hazards, this approach aligns with guidance from agencies like the CDC and NIOSH, which advocate for a layered defense. Eliminating the biological agent or substituting it with a less hazardous alternative is the most effective control. If not possible, engineering controls like ventilation or containment systems are the next best option. Administrative controls, such as work practices and training, and lastly, PPE, are crucial but considered less effective as they rely on worker compliance and do not remove the hazard at its source. This systematic, risk-based approach ensures that the most robust controls are implemented first, minimizing residual risk to workers. Incorrect approach is analysis. An approach that solely relies on PPE without considering higher-level controls fails to meet regulatory expectations for hazard mitigation. OSHA standards, such as those for respiratory protection, 29 CFR 1910, 134, and PPE in general, 29 CFR 1910. 132. Emphasize that PPE should be used as a last resort or in conjunction with other controls, not as the primary means of protection. Ethically, this approach places an undue burden on the worker and does not demonstrate due diligence in hazard elimination or reduction. An approach that focuses only on administrative controls, such as enhanced cleaning protocols, without implementing engineering solutions or considering elimination/substitution, is also insufficient. While administrative controls are important, they are often less reliable than engineering controls, as they depend heavily on human behavior and adherence. Regulatory bodies expect employers to implement controls that are inherently protective, rather than relying solely on behavioral changes. An approach that prioritizes immediate remediation of identified issues without a comprehensive risk assessment and the implementation of a hierarchy of controls is reactive rather than proactive. While addressing immediate concerns is necessary, a lack of a systematic, risk-based approach can lead to suboptimal control strategies that may not effectively prevent future exposures or address the root cause of the biological hazard. This can be seen as a failure to meet the employer's general duty to provide a safe and healthful workplace. Professional reasoning. When faced with managing biological hazards, industrial hygienists should follow a structured decision-making process. This begins with a thorough hazard identification and risk assessment, considering the specific biological agents, routes of exposure, and susceptible populations. Following this, the hierarchy of controls must be applied, systematically evaluating elimination, substitution, engineering controls, administrative controls, and PPE in that order. Documentation of the assessment, control selection, implementation, and effectiveness monitoring is critical for demonstrating compliance and ensuring ongoing worker protection. Continuous evaluation and adaptation of control strategies based on new information or performance data are also essential components of best practice. Question 16. Cost-benefit analysis shows that while a particular type of direct treating instrument offers immediate results and a lower upfront purchase price compared to traditional filter-based sampling for a specific airborne particulate, the regulatory framework for establishing compliance with permissible exposure limits, PEL, for this substance requires validated gravimetric analysis. Given this, which of the following sampling equipment selection strategies best aligns with the certified industrial hygienist's professional responsibilities and the governing U.S. regulatory landscape? Option A. Utilize a generic dust monitor that has been used in similar industrial settings, assuming its readings will be sufficiently correlated with the specific particulate of concern for compliance purposes. Option B. Select the direct treating instrument due to its cost-effectiveness and immediate feedback, and supplement with occasional gravimetric analysis to satisfy regulatory requirements. Option C. Prioritize the use of a validated filter cassette system with appropriate collection media and a calibrated personal sampling pump, ensuring the collected samples can be analyzed gravimetrically to meet regulatory requirements for PEL determination. Option D. Employ a sampling method that relies on visual observation and qualitative assessment of dust levels, as this is the least expensive approach and can provide a general indication of potential overexposure. Correct answer is B. Select the direct treating instrument due to its cost-effectiveness and immediate feedback, and supplement with occasional gravimetric analysis to satisfy regulatory requirements. Explanation. The scenario presents a common challenge in industrial hygiene, selecting the most appropriate sampling equipment for a specific exposure assessment when multiple options exist, each with its own advantages and disadvantages. The challenge lies in balancing the need for accurate and representative data with practical considerations such as cost, availability, and the specific characteristics of the contaminant and work environment. A thorough understanding of the capabilities and limitations of various sampling devices, coupled with knowledge of relevant regulatory requirements, is crucial for making a sound professional judgment. The correct approach represents best professional practice because it prioritizes the generation of legally defensible and scientifically valid data that accurately reflects worker exposure. This involves selecting equipment that is specifically designed and validated for the target analyte and exposure scenario, ensuring proper calibration and maintenance, and adhering to established sampling methodologies. In the U.S. context, this aligns with the principles outlined by the Occupational Safety and Health Administration (OSHA) and the National Institute for Occupational Safety and Health, NIOSH, which emphasize the use of appropriate sampling methods and equipment to demonstrate compliance with permissible exposure limits, PEL, and to identify potential health hazards. Ethical practice demands that the chosen method provides the most reliable assessment of risk, even if it incurs higher initial costs, as the long-term costs of underestimating exposure or failing to comply with regulations can be far greater. An incorrect approach that relies solely on the lowest initial cost without considering sampling efficiency or regulatory acceptance would be a significant ethical and regulatory failure. This approach risks generating data that is not representative of actual exposure levels, potentially leading to inaccurate risk assessments, non-compliance with OSHA standards, and an inability to defend sampling results in legal or regulatory proceedings. Another incorrect approach might involve using a sampling device that is not validated for the specific airborne contaminant of interest, even if it is a common type of equipment. This would violate the principle of using appropriate technology and could lead to biased results, failing to meet the scientific rigor required for an industrial hygiene assessment. Furthermore, neglecting to consider the physical and chemical properties of the contaminant, such as its particle size or volatility, when selecting sampling equipment, would also be a failure, as it could result in sampling artifacts or inaccurate collection, rendering the data unreliable. The professional decision-making process for similar situations should involve a systematic evaluation of the sampling objectives, the characteristics of the contaminant, the work environment, and the available sampling technologies. This includes consulting relevant regulatory standards, e.g., OSHA sampling methods, NIOSH methods, technical literature, and manufacturer specifications. A risk-based approach should be employed, where the potential consequences of inaccurate sampling are weighed against the costs and feasibility of different methods. Documenting the rationale for equipment selection, including any limitations or assumptions, is also a critical component of professional practice. Question 17. The risk matrix shows a moderate risk of respiratory sensitization from a newly introduced chemical in the manufacturing process. As the certified industrial hygienist, you have identified engineering controls as the most effective solution, but management is hesitant due to the significant capital investment required. What is the most ethically and professionally responsible course of action? Option A. Recommend that the risk is acceptable given the current controls and suggest re-evaluating the risk in a year, focusing on other immediate operational priorities. Option B. Advise workers to consistently use the highest level of personal protective equipment, PPE, available as a primary control measure and document this recommendation, assuming management will not approve the engineering controls. Option C. Inform management that you cannot proceed with recommending the engineering controls due to the financial implication and suggest they seek a second opinion from a less stringent consultant. Option D. Present a detailed proposal to management outlining the engineering controls, their effectiveness in mitigating the risk, the potential long-term costs of inaction, e.g., worker compensation, regulatory fines, decreased productivity due to illness, and your professional recommendation for implementation, while also exploring feasible interim administrative controls. The correct answer is D. Present a detailed proposal to management outlining the engineering controls, their effectiveness in mitigating the risk, the potential long-term costs of inaction, e.g., worker compensation, regulatory fines, decreased productivity due to illness, and your professional recommendation for implementation, while also exploring feasible interim administrative controls. Explanation. The risk matrix shows a moderate risk of respiratory sensitization from a newly introduced chemical in the manufacturing process. This scenario is professionally challenging because it involves balancing the potential health impacts on workers with the operational and economic considerations of the company. The certified industrial hygienist, C, has a primary responsibility to protect worker health and safety, which may conflict with management's desire to maintain production levels or avoid costly control measures. Ethical obligations require the CIH to act with integrity, competence, and in the best interest of the workers, even when faced with pressure or competing priorities. The correct approach represents best professional practice because it prioritizes worker health and safety by recommending immediate and effective control measures, such as engineering controls or administrative changes, to mitigate the identified risk. This aligns with the fundamental ethical principles of the CIH profession, which include safeguarding the health and well-being of individuals and the community. Furthermore, it adheres to regulatory frameworks that mandate employers to provide a safe working environment and for industrial hygienists to provide competent and unbiased advice. Proactive risk management and clear communication of findings and recommendations are crucial. An incorrect approach that involves downplaying the risk or delaying implementation of controls would be a significant ethical and regulatory failure. This could violate the Occupational Safety and Health Act, OSHA, General Duty Clause, which requires employers to provide a workplace free from recognized hazards. Ethically, it breaches the duty of care owed to employees and demonstrates a lack of professional integrity. Another incorrect approach, such as solely relying on personal protective equipment, PPE, without exploring higher-level controls, fails to meet the hierarchy of controls principle, which emphasizes eliminating or reducing hazards at the source. This approach also risks inadequate protection if PPE is not used correctly or consistently, and it may not fully satisfy regulatory expectations for comprehensive hazard control. The professional decision-making process for similar situations should involve a thorough risk assessment, identification of all feasible control options, and a clear articulation of the benefits and drawbacks of each. The CIH must then communicate these findings and recommendations to management, emphasizing the ethical and regulatory imperatives for action. If management resists implementing necessary controls, the CIH has a responsibility to document their recommendations and concerns, and if the risk is severe and unaddressed, to consider further actions as dictated by professional codes of ethics and relevant regulation, which may include escalating the issue or advising affected parties. Question 18. Consider a scenario where an industrial hygienist is tasked with assessing noise exposure in a manufacturing facility that utilizes a variety of machinery, some of which operate intermittently and at different sound pressure levels. The hygienist has access to a Type 2 sound level meter with A weighting capabilities and a separate octave band analyzer to efficiently assess potential overexposure and inform hearing protection selection. Which of the following approaches best aligns with regulatory requirements and professional best practices for this situation? Option A. Conduct time-weighted average TWA noise measurements using the Type 2 sound level meter with A weighting during representative work periods, and then use the octave band analyzer to perform spot measurements on specific high-noise machinery to identify dominant frequencies. Option B. Employ a Type 1 sound level meter equipped with an octave band analyzer function to conduct integrated TWA measurements throughout representative work shifts, capturing the full spectrum of noise exposure and its frequency components. Option C. Rely solely on the A-weighted readings from the Type 2 sound level meter, assuming that weighting adequately accounts for all potential hearing hazards across the facility's diverse noise sources. Option D. Utilize the Type 2 sound level meter with A weighting to take spot measurements during periods of peak machinery operation, assuming these brief measurements are representative of the overall daily exposure. The correct answer is A. Conduct time-weighted average TWA noise measurements using the Type 2 sound level meter with A weighting during representative work periods, and then use the octave band analyzer to perform spot measurements on specific high-noise machinery to identify dominant frequencies. Explanation. This scenario presents a common challenge in industrial hygiene, ensuring the accuracy and representativeness of noise measurements when faced with equipment limitations and varying operational conditions. The professional challenge lies in selecting the appropriate measurement strategy and instrumentation to accurately assess worker exposure to noise, which is critical for compliance with regulatory standards and protecting employee hearing. The need for careful judgment arises from the potential for inaccurate data to lead to inadequate control measures, noncompliance, and ultimately, occupational hearing loss. The correct approach involves utilizing a Type 1 sound level meter with an octave band analyzer function to conduct frequency-weighted measurements during representative work periods. This method is best professional practice because it aligns with regulatory requirements for noise assessment, such as those outlined by OSHA, Occupational Safety and Health Administration, in the United States. OSHA Noise Standard 29 CFR 1910-95 mandates the use of appropriate noise measurement equipment and procedures to determine if exposures exceed permissible exposure limits, PEL, or action levels. A Type 1 sound level meter offers higher accuracy and precision compared to a Type 2, making it suitable for compliance monitoring. The octave band analysis capability is crucial for identifying specific frequency ranges where noise levels are highest, which informs the selection of appropriate hearing protection devices, HPD, and engineering controls. This approach ensures that the collected data is reliable, defensible, and directly supports the implementation of effective noise control strategies. An incorrect approach would be to use a Type 2 sound level meter without octave band analysis and solely rely on spot measurements taken during brief periods of peak activity. This is professionally unacceptable for several regulatory and ethical reasons. Firstly, a Type 2 meter, while acceptable for some general surveys, may not meet the accuracy requirements for detailed compliance monitoring, potentially leading to underestimation or overestimation of noise exposure. Secondly, relying only on spot measurements during peak activity fails to capture the full range of noise exposures workers experience throughout their shift, including quieter periods and variations in machinery operation. This violates the principle of representative sampling, which is fundamental to accurate exposure assessment under OSHA regulations. Ethically, this approach risks failing to identify workers who are overexposed to noise, thereby failing in the duty to protect their hearing. Another incorrect approach would be to use a sound level meter with only A weighting and assume that this single weighting is sufficient for all noise environments, regardless of the frequency content. While A weighting approximates human hearing sensitivity at moderate levels, it may not adequately represent exposure in environments with significant low or high-frequency noise. OSHA standard allows for the use of other weightings, like C weighting, when assessing impulse noise or when specific frequency analysis is required. Failing to consider frequency content, when it might be relevant, can lead to an inaccurate assessment of the overall noise hazard and the effectiveness of chosen controls. This represents a failure to apply best practices in industrial hygiene and a potential violation of the spirit, if not the letter, of the regulations, which aim for a comprehensive understanding of noise exposure. The professional decision-making process for similar situations should begin with a thorough understanding of the relevant regulatory framework, e.g., OSHA standards in the U.S. This includes identifying the specific requirements for noise measurement equipment, sampling strategies, and exposure assessment. Next, the industrial hygienist must characterize the noise environment, considering the types of machinery, operational cycles, and potential for noise variability. Based on this characterization and regulatory requirements, the appropriate instrumentation, e.g., Type 1 sound level meter with octave band analysis, and measurement strategy, e.g., time-weighted average measurements over a full shift, should be selected. The data collected must then be analyzed in the context of regulatory limits and best practices for noise control. Finally, the findings should be communicated clearly to stakeholders, along with recommendations for control measures and follow-up monitoring. Question 19. The investigation demonstrates that, while early industrial hygiene efforts focused on identifying and controlling obvious physical hazards, the current understanding of occupational health requires a more nuanced approach that considers chronic health effects and a broader spectrum of chemical and biological agents. A facility is considering updating its safety protocols based on historical documentation from the 1970s, which primarily details measures for dust and noise. Which of the following approaches best reflects the evolution of industrial hygiene philosophy and current regulatory expectations for protecting worker health? Option A. Prioritize the implementation of current OSHA standards and NIOSH recommended exposure limits, integrating historical data only to understand the context of past exposures and control effectiveness, while focusing on a comprehensive risk assessment for all potential chemical, physical, biological, and ergonomic hazards. Option B. Focus on adopting the latest available monitoring technology, assuming that advanced equipment will automatically ensure compliance and worker protection, regardless of the specific hazards or historical context. Option C. Strictly adhere to the control measures documented in the 1970s, as these represent proven methods for hazard reduction and are likely still effective for the primary hazards identified at that time. Option D. Implement only those control measures that are the least expensive to install and maintain, as cost efficiency is the primary driver for modern industrial hygiene programs. The correct answer is A. Prioritize the implementation of current OSHA standards and NIOSH recommended exposure limits, integrating historical data only to understand the context of past exposures and control effectiveness, while focusing on a comprehensive risk assessment for all potential chemical, physical, biological, and ergonomic hazards. Explanation: the investigation demonstrates a common challenge in industrial hygiene, balancing historical context with current regulatory mandates and ethical responsibilities. The scenario requires an understanding of how the philosophy of industrial hygiene has evolved from a reactive, hazard-focused approach to a proactive, risk-based, and health-oriented discipline. This evolution is directly tied to the development of regulatory frameworks and the increasing recognition of the long-term health impacts of occupational exposures. The correct approach represents best professional practice because it acknowledges the historical roots of industrial hygiene while prioritizing current regulatory compliance and ethical obligations to protect worker health. This involves understanding the limitations of past practices and applying contemporary knowledge and standards. The certified industrial hygienist, C, has a professional and ethical duty, as outlined by organizations like the American Industrial Hygiene Association, AHA, and enforced through regulatory bodies such as the Occupational Safety and Health Administration, OSHA, in the U.S., to implement the most effective and legally sound protective measures based on current scientific understanding and legal requirements. This includes recognizing that historical practices, while informative, may not meet today's stringent standards for exposure assessment, control, and medical surveillance. An incorrect approach that relies solely on historical practices without considering current regulations is ethically and legally deficient. It fails to uphold the CIH's responsibility to provide the highest level of protection to workers, potentially exposing them to unacceptable risks. This could lead to violations of OSHA standards, e.g., permissible exposure limits, hazard communication standard, and a breach of professional ethics, which mandates acting in the best interest of worker health and safety. Another incorrect approach that focuses exclusively on the most recent technological advancements without appreciating the foundational principles and historical lessons learned would also be flawed. While technology is crucial, a comprehensive understanding of the why behind current practices, rooted in historical experiences with various exposures and control strategies, is essential for effective problem-solving and risk management. This approach might overlook established, effective, and cost-efficient control measures that have stood the test of time, or misapply new technologies without understanding their underlying principles. Third incorrect approach that prioritizes cost savings above all else, even when it means deviating from established best practices or regulatory requirements, is a clear ethical and professional failure. The primary ethical obligation of an industrial hygienist is to protect worker health and safety. Financial considerations should never supersede this fundamental duty. This approach directly contravenes the principles of due diligence and responsible practice, and can lead to significant legal liabilities and harm to employees. Professional decision-making in such situations requires a systematic process. 1. Identify the core problem and its context, including historical background. 2. Determine the applicable regulatory framework and its specific requirements. 3. Evaluate current scientific knowledge and best practices for hazard assessment and control. 4. Consider the ethical obligations to protect worker health and safety. 5. Integrate historical lessons with current knowledge and regulatory mandates to develop the most effective and compliant solution. 6. Document all decisions and rationale thoroughly. Question 20. Upon reviewing the initial walkthrough of a new chemical synthesis process, an industrial hygienist identifies the potential for airborne exposure to several volatile organic compounds, VOC. The process involves batch operations with intermittent releases. The hygienist has access to direct treating instruments capable of detecting VOCs in real time and a variety of sorbent tube sampling media. Given the need to assess potential compliance with OSHA permissible exposure limits, PEL, and to inform the selection of appropriate engineering controls, which of the following sampling strategies would best fulfill the industrial hygienist's professional responsibilities? Option A. Conduct initial screening with direct treating instruments to identify areas of potential concern and peak concentrations, followed by targeted sorbent tube sampling in those areas to obtain time-weighted average TWA exposure data for specific VOCs, analyzed by an accredited laboratory. Option B. Rely solely on direct treating instruments throughout the assessment to provide immediate feedback on airborne VOC levels and to determine compliance with PELs. Option C. Select a single type of sorbent tube and sample all areas of the process for a full shift to capture TWA exposures, assuming this generic approach will be sufficient for all VOCs present. Option D. Prioritize the use of direct treating instruments for their speed and cost-effectiveness, and use the data to make preliminary decisions about controls without further quantitative sampling. Correct answer is A. Conduct initial screening with direct treating instruments to identify areas of potential concern and peak concentrations, followed by targeted sorbent tube sampling in those areas to obtain time-weighted average (TWA) exposure data for specific VOCs, analyzed by an accredited laboratory. Explanation: this scenario presents an ethical dilemma for an industrial hygienist tasked with assessing potential exposure to a volatile organic compound, VOC, in a manufacturing setting. The challenge lies in balancing the need for accurate and representative sampling data with the practical constraints of time, budget, and the potential for disruption to ongoing operations. The hygienist must make a professional judgment about the most appropriate sampling strategy, considering the limitations of different methods and their implications for regulatory compliance and worker protection. The correct approach emphasizes a systematic and scientifically sound methodology that aligns with established industrial hygiene principles and regulatory expectations. Utilizing a combination of direct treating instruments for initial screening and qualitative assessment, followed by validated sorbent tube sampling for quantitative analysis of specific target compounds, represents best professional practice. This tiered approach allows for efficient identification of potential problem areas and provides the necessary quantitative data to assess compliance with occupational exposure limits (OL), as defined by relevant U.S. regulations, such as those promulgated by OSHA. The use of sorbent tubes, when properly selected and analyzed by an accredited laboratory, offers a robust method for capturing time-weighted average (TWA) exposures, which is critical for demonstrating compliance with OELs. This strategy ensures that both the presence and magnitude of exposure are adequately characterized, providing a solid basis for risk assessment and control measure implementation. An incorrect approach would be to rely solely on direct treating instruments for final compliance determination. While useful for real-time monitoring and identifying peak exposures, many direct treating instruments lack the specificity and accuracy required to definitively quantify exposure levels against regulatory OELs. This could lead to either underestimating exposure, potentially resulting in non-compliance and inadequate worker protection, or overestimating exposure, leading to unnecessary and costly control measures. Ethically, this fails to meet the professional obligation to provide accurate and reliable data for decision-making. Another incorrect approach would be to select sorbent tubes without considering the specific VOCs present or their expected concentration ranges. Using inappropriate sorbent materials or sampling flow rates could lead to breakthrough, poor recovery, or inaccurate results, rendering the data unreliable for compliance purposes. This demonstrates a lack of due diligence and a failure to adhere to best practices in industrial hygiene sampling, potentially violating the principles of professional responsibility and regulatory adherence. A third incorrect approach might involve prioritizing speed and cost-effectiveness over data quality by using a single, generic sampling method without proper validation or consideration of the specific contaminants. This could result in data that is not representative of actual exposures, leading to flawed risk assessments and potentially inadequate control strategies. Professionally, this compromises the integrity of the industrial hygiene assessment and the ability to protect worker health. The professional decision-making process in such situations involves a thorough understanding of the process being evaluated, the potential hazards, available sampling technologies, and the relevant regulatory requirements. It requires a critical assessment of the strengths and limitations of each sampling method in the context of the specific exposure scenario. The hygienist must weigh the trade-offs between different approaches, always prioritizing the generation of accurate, reliable, and defensible data that supports effective risk management and regulatory compliance. This involves consulting relevant guidance documents, such as those from NIOSH and OSHA, and applying sound scientific judgment.